This is Unit 8, Lesson 4, Video 1. So we are going to look at what is called the combined gas law. And this combines Boyle's and Charles' law into one cohesive equation. So if you recall, Boyle's law was P1 over V1 is equal to P2 times V2. Charles' law was V1 over T1 is equal to V2 over T2. So in these, we combine these two, and you'll notice that the V's are both on the same line. They're both in the numerator, but the P's are both in the numerator, T's are in the denominator, and that gives us this gas law. P1 over V1, P1 times V1 over T1 equals P2, V2 over T2. So here, the P units, the pressure units have to be the same. The temperature units must be in Kelvin, and the volume units must be the same. So let's look at an example problem. Here we have a sample of neon gas occupies a volume of 42.5 liters at 75.5 degrees Celsius and 760 torr. What will be the new volume? So I'm going to circle that one. The pressure is in 2.5 atmospheres and the temperature increases to 459 Kelvin. So with this, the tricky thing is keeping track of everything. We have 6 variables: P1, V1, T1, P2, V2, and T2. Now we just have to match everything up. One of them is going to be the unknown that we're solving for, and the rest of them are going to be given. So our pressure was 760 point torr. Our volume was 42.5 liters, and our temperature was 75.5 degrees Celsius. We want to know what will be the new volume, so there is our question mark. There's what we're going to be solving for. The pressure increases to 2.5 atmospheres, and the temperature increases to 459 Kelvin. So if we go back up here, our pressure units have to be the same. They are not the same. Now, we have to go back and look, and if we see that, we can see that 760 torr is equal to 1 atmosphere. But I'm going to make those significant, so 1.00 atmospheres. Since we had 3 significant figures here, we should have 3 significant figures in our answer. Our volume units are okay. They have to be the same, so our answer will be in the same units, liters. But our temperatures have to be in Kelvin. Well, this T2 is, but T1 is not. So we have to add 273 Kelvin to the first one to give us 348.5 Kelvin. So now that we have all of our variables defined, we can put them into our equation. P1, which is 1.00 atmospheres, times V1, 42.50 liters, all over T1, 348.5 Kelvin, is equal to P2 times V2 all over T2. So in order to get rid of this, we have to get V2 by itself. A lot of people like to cross multiply, and that is fine. So we can take this and set it equal to this. So we can get 1.00 atmospheres times 42.5 liters times 459 Kelvin is equal to 2.5 atmospheres times V2 times 348.5 Kelvin. So to get V2 by itself, I'm going to multiply by both sides by 2.5 atmospheres, and 348.5 Kelvin. That crosses off our atmospheres and our Kelvin on that side. Over here, this looks really complicated, but it's just simple arithmetic. Our atmosphere units cross out and our Kelvin, we're left with liters. So in our calculator, just be careful with these. 1.00 times 42.5 equals times 459 equals. And we can divide that, but make sure that you use either parentheses around these two. So 2.5 times 348.5, close parentheses, so we can get the right answer. Or if we multiply all these out and hit equals, divide by 2.5, hit equals, divide by 348.5 equals. We get the same answer. So the two significant figures is 22 liters. So it really went down. So we increased the temperature, but we really increased the pressure. And it went way down, almost cut in half. Let's look at number 2. A sample of chlorine gas has a volume of 900.0 milliliters at STP. Remember standard temperature and pressure? That was 1.00 atmospheres and 273 Kelvin. At what temperature in degrees Celsius will the volume be 500 milliliters and the pressure be 0.950 atmospheres? So P1, V1, and T1, P2, V2, and T2. So our first pressure was at STP, 1.00 atmospheres. It was 900.0 milliliters and 273 Kelvin. We're looking for the temperature at which the volume decreases to 500 milliliters and our pressure has slightly decreased to 0.950 atmospheres. So I'm going to plug these values all into my equation. P1 times V1 all over T1 is equal to P2 times V2 all over T2. Then I can cross multiply these to get rid of the fraction. So 1.00 atmospheres times 900.0 milliliters times T2 is equal to 0.950 atmospheres times 500.0 milliliters times 273 Kelvin. I want to get T2 by itself, so I'm going to divide both sides by these to get rid of them. That allows us to cross out those, and we're left with T2. And since this is 1 atmosphere, the units cross out, but we know that we don't, anything divided by 1 is itself, so we don't really have to worry about that. So 0.950 times 500.0 times 273, and I'm going to hit equals and divide that by 900.0. And I get 144 Kelvin to significant figures. But I want this to be in degrees Celsius. So that means I have to subtract 273 from that. 144 minus 273 gives me negative 129 degrees Celsius. So that is pretty cold.